welcome to the third virtual colloquium, which seems to be quite successful so far. So it's a pleasure to have Tankut Khan with us. And he is one of our own. He is a postdoctoral fellow at ITS CUNY. And so his short bio is that he was undergrad at Berkeley. And after that, he went to do a PhD at Chicago with Paul Wigman on quantum Hall on curved spaces and many other things related to that. And then he moved to Simon Center as a postdoc, where we overlapped for a couple of years. And subsequently, we both moved to CUNY. Like he's in Midtown and I'm at Harlem. So it's a pleasure to have Tankut. And now he's going to talk about dynamics of gated recurrent neural networks, a very interesting topic that is kind of at the initial stages of understanding machine learning in a more fundamental way. So it's like more like how bring physics to machine learning rather than bring machine learning to physics. So Tankut, it's yours now.
Excellent. Thanks a lot, Suram. It's really nice to be here. It's just wonderful to have an audience and to be with my fellow CUNY people. Yeah, so you said it exactly right. The big picture behind the work that I'm going to talk about is that there's this extremely stunning kind of results we're seeing, especially in the news, about machine learning and what AI is doing, artificial intelligence is doing these days, and there remains a sort of really basic lack of understanding, which physics and the tools from physics can really help address. And that's exactly where I hope to situate this talk, is using physics and physics approaches to understand machine learning. And in particular, so the approach, the particular kind of neural network I'm interested in are recurrent neural networks, and I'll get into that right now. So, oops. Okay, so just a quick outline to get a sense of what to expect. Part one, I'll try to do a selected review of the past, present, and future of recurrent neural networks, where they came from, what they can do now, and what still needs to be done, perhaps. And no equations in this part. This is like casual conversation to an extent. In part two, I'll kind of get in the weeds, because maybe you're hungry to understand what exactly I mean by all of these things. What is an RNN? I'll explain it in part two. And I'll explain how we train them, how they learn, and what are some basic obstacles in doing this, and what physics can teach us. And the last part will be a review of very recent results that I'm excited about, that had to do with a thing called gated RNNs, which I'll explain when we get there. And of course, if there's any questions, really feel free to ask. I'm open to more interactive seminar. But if you just want to sit back and relax and let the talk wash over you, that's fine too. Whatever. So first, I should mention my collaborators. This is work that was done in very close collaboration with Kamesh Krishnamurti, who's a postdoc at Princeton. Also David Schwab, who's at the ITS. And you can see our work. It's in these two papers. Mostly, I'll be speaking about the top one today when I get there. Okay, so part one, the selected tour of history. And I'm going to start it with an allegory to motivate studying learning from a physicist's perspective. So if you know where the pictures on the left come from, this is from a movie, They Live, by John Carpenter. And the basic premise is this drifter arrives in some town and he gets his hand on these glasses. And whenever he puts on the glasses, he sees the world for what it truly is. And in this case, it's run by aliens who are trying to subjugate humans. But I think of this as a sort of an allegory for scientific reasoning. without the glasses, we can see a bunch of falling apples. We say, okay, cool, apples falling. But we put on the glasses, apply our reasoning and scientific thinking, and we arrive, at least Newton rather, arrives at the universal law of gravitation, right? And of course, once you have the glasses, and once this guy had the glasses, he decided to, act. Like, yes, look at all the things I can do. Look at all the aliens I can see. Let's change the world for the better. In his case, get rid of aliens. In the physicist's case, discover more fundamental laws, apply them from universal law of gravitation, get to relativity, something like this. But of course, the question is, aren't you curious how the glasses work? Of course, and this is the basic motivator, at least for me. There's a question of how are we able to reason in the way that we can? So this is really coming back to understanding, how does the brain work, right? That's the most natural starting point. If I want to understand these glasses, right? How does cognition work? But of course, I think it's uncontroversial to say brains are complicated. Even in 1898, Santiago Ramon y Cajal was doing these very intricate drawings of neurons, identifying their differentiated structure. And back then, even, it was clear these are incredibly complicated structures. And to understand how they enter in the brain and interconnect, in 2020, just very recently, the fly connectome was mapped. So there's a sense of how the entire wiring of the fly brain works, but it's a lot of details. And this is sort of anathema to the physicist's approach in general. So what does it mean to understand the brain? What do I mean when I say I want to understand the brain? I think it's best to invoke some historical figures to help motivate my story. So this was one of the pioneers of mathematical biology, Nicholas Reshevsky, and he advocated in just perfect fashion, as a physicist should, for simplified models of idealized biological processes. So applied to the brain, the idea would be to think about what makes a neural network, distill those principles to some basic abstract components, and study that simplified, idealized model. And of course, the models must be quantitative, and they must make contact with experiments. So this is the question in physics, right? How simplified can you make a model? I think, as Arnold liked to say, what's the simplest non-trivial example, for instance, of a brain? Okay, that's it's sort of the idea here. And I can go back to the previous slide. So what are some salient elements of a brain? Is that they're complex networks. They're highly interconnected, highly interacting, but each component, each neuron, is relatively simple. And also, they're dynamical systems. They process information in time and dynamically. Okay, so we'll see some examples of that and how it's manifest in the idealized neural networks. Okay, so to begin, really coming out of this school of thought that was started by Reshevsky, in 1943, McCullough and Pitts wrote this extremely ambitious paper, in which they really started with exactly this approach. What is the simplest model of a neuron? So for instance, a neuron takes some inputs from all of the connections, integrates them, maybe adds them up, and then outputs something. and it's either 1 or it's 0. So they were thinking of really neural networks as logical circuits, but it was very early work in this direction, and it made it a crucial leap, maybe not a leap, but a crucial insight, which is that brain function or cognition is equivalent to computation. And this is even reflected in a comment by one of the authors, McCullough, in which he claimed that his intention, what we thought we were doing, was treating the brain as a Turing machine, and that literally didn't necessarily succeed. But the approach that brain function cognition is computation is this great abstraction that allows you to now think about cognition on a computer, okay? Because you've abstracted really what is a process? What is a brain process? It's some kind of information processing device. It takes an input like stimulus and produces an output, some behavior. And the idea in this particular selection from history, I'm showing Rosenblatt's perceptron, which was developed in 1957. And shown here quite impressively. This isn't Rosenblatt working on it, but it was intended to be an actual machine, which takes some input and classifies maybe some pattern, classifies it as, this wasn't what they used, but for instance, if you see a cat or a dog, you want your machine to get an input of a cat or a dog and then output either cat or dog, 1 or 0, depending on what it is. So this took the idea of neural networks, abstract neural networks, and tried to make them learn. And this is one of the most remarkable facts, I think, of the brain, which is that it can learn. It can learn things. We can learn the difference between cats and dogs and form general categories like this. So applying some kind of learning rules to make an artificial neuron know the difference between cats and dogs. And so, yeah, I showed this picture of someone working on the perceptron in 1960. And this is what it would look like to work on a perceptron today. It's just not as impressive, I think. I liked showing this huge device with a bunch of wirings, but I pulled this off of Wikipedia, obviously. That's Jimmy Wales. Yeah, so it's very simple to do on your laptop. It's kind of a simple little algorithm. Okay, so now we have these artificial neural networks, sort of a distilled, some artificial neuron, and now we're still missing the dynamical aspect. And this was really pioneered in the 70s, which was also known as the AI winter, by Grossberger, in which he thought about learning in recurrent networks of artificial neurons. And what does recurrent mean? It's just that before we had this, oh, I'll use my pointer. We had this neuron which receives inputs and spits out some output, some 1 or a 0. But now recurrence means that the neuron's output is then fed back into the input. And more generally, for a network of neurons, recurrence means that the output of the network is fed back to the input of the network. And this is really just a way of saying that now we're thinking of neural networks as dynamical systems. And this will become clear later in the talk, what I mean by that. And so importantly now, there's two processes. Now, first, there's the short-term memory. This is just the nomenclature. The short-term memory is the dynamics of the neural network. So the neural activity. It's how often this neuron is firing or something like this. And then we have long-term memory, which is the learning dynamics of the weights. So the weights, what I mean is that the neuron sees different inputs and it pays attention to them differently. So for instance, just schematically, this input, this neuron treats as very important and it pays attention to it more. That weight is higher, it's weighted more. This one, not so much. And what learning in neural networks boils down to is understanding which inputs to pay more attention to, which to pay less attention to. So adjusting the weights.
So Tankut, I have a question. So the way you are presenting, so you're saying that memory is kind of part of learning, right? In the sense, memory is not separate from learning in some sense. So it's like, it's just the fact that you're dynamically recognizing a pattern is basically accessing a memory in some way. So but
yeah,
means in a computational learning process, like there is a storage which is kind of different from a dynamical system that you are computing.
Yeah, and this is, so I think maybe in my next slide, this is hopefully made really kind of clear how, in what sense, memory is a dynamical process. If that was
okay.
Sort of,
yeah.
So right. So this, now we have this recurrent networks. They turn these neural networks, these networks of neurons, into dynamical systems, and the takeaway is that dynamical systems can be used for computation. And we know that that's true because our brains are dynamical systems, the neural networks in our brains.
Maybe I want to rephrase my question in a way that so memory seems to be intuitively something that is rigid, right? Some aspect of your wiring that is rigid and unchanging. But at the same time, things are dynamically changing in a neural network. So that's what I wanted to distinguish. That okay, maybe I will wait for your slide to complete.
So maybe in this case, it's a separation of timescales. And this is what long-term memory versus short-term memory means. So maybe I'll go over this and I'll try to get back to that point.
Okay.
So this is, I think, a really nice and crisp example of how dynamical systems specifically can compute. And it's Hopfield's model for associative memory, which was written in 1982. So the idea is that information, or maybe a pattern or something like this, is stored in attractors or fixed points. And this is crucially a property of recurrence because its attractors show up in dynamical systems, and with a large N, meaning you need many neurons to make this kind of thing work. So the idea in this picture is that some input, maybe seeing one picture of a cat, will land you somewhere here in this particular basin of attraction. And if you land here, you're going to flow to point B. And point B, that's a fixed point. And that is, for instance, your output, which says cat. If it's a different input, like a dog, you end up in this basin and you flow to this point. So there's two kind of time scales that are at play here. One is just the time scale of this flow. That's short-term memory. That's you receive some input and your neural network dynamically flows to a fixed point. Long-term memory would be the adjusting of the weights to create these basins of attraction in the first place. Something like that.
So the more information you learn, the more fixed points you are creating.
Yeah, and then there's a very interesting question about what's the capacity of these networks. How many patterns can they possibly learn? How many fixed points can they learn? And it's typically, it scales with the number of neurons. That's a side point. There's a very, very rich, interesting story behind just this model. So in this sense, the takeaway here, which I want to convey, is that the dynamics itself is essential to the mechanism which implements a computation. Because the computation is storing of patterns and retrieving them later based on some input. And the mechanism is basins of attraction with fixed points that encode that particular memory. So in a similar vein, instead of just isolated points here, here, and here, you can have a line attractor. So a line attractor, what it means is, for instance, if you're stuck at point 1, you receive some kick out to 2, then you're going to flow and come back down to 3. And you could just move along the line attractor and it wouldn't cost any kind of energy, meaning it wouldn't induce any activity because they're all fixed points. So these kind of structures, they were proposed to be implicated in how the brain keeps the eye still. Oh, I forgot. There should be keeps the eyes still. Basically, any computation, any process which requires really long, short-term memory. So, for instance, like where the eye is, which direction it's pointing at, you might expect, or in the very least, this kind of dynamical attractor would accomplish this goal. So this is one mechanism to realize this kind of computation. And this is interesting, and I bring it up because it comes up when I speak later about gated RNNs.
So is this a proposed theory or experimentally verified mechanism?
It is a theory, and then there's experiments on a sort of cousin of this line attractor, which is known as a ring attractor. So the proposal is that it's not really just phase space that has this line attractor. It's actually physically visible in the neuron space. So the neurons wire in some kind of ring pattern. But I think it's still, there's some evidence that this is used and implemented in real networks, in real neurons. Mm-hmm. Right, and I'm going to finish this possibly idiosyncratic review of the history of RNNs with Hochreiter and Schmidhuber's long short-term memory. So this is what I mentioned before. Long short-term memory. This paper was really the breakthrough which accelerated modern machine learning applications of RNNs. And they introduced one crucial ingredient, which was gating interactions. And this cartoon, it sort of illustrates what I mean by gating interaction. So you have your neural network. It has wirings and connections. And you introduce an additional variable, in this case, these gates, which can be open or closed. So you can selectively let information flow or stop it in its tracks. And this gives you really long dynamics, long time scales in your dynamics. That's long short-term memory. And it happens to make training of neural networks, recurrent neural networks, possible. Whereas before it was extremely hard. With gating, it allows incredible strides. So to get to what RNNs can do and what kind of strides were made after gating is introduced, it might be useful to think about what they might be good for just in principle. And this is an important aspect of thinking about learning algorithms and neural network architectures. It's a question of inductive bias. Like, just by virtue of the architecture and the structure, what kind of problems might they be good at? And really, there's no crisp, and there's a bunch of rules of thumbs, let me put it this way, in deciding this. A lot of rules, a lot of experience, and a lot of rules of thumb. So for RNNs, it's very natural if you have to process data sequentially or with temporal extent. Because you have a dynamical system, if your input is, for instance, a sentence, you can, invent a time axis in a sentence and read the sentence in time. More concretely, if it's a time series like stock prices, it's very natural to use an RNN to think about, to receive input has temporal extent in time. Another thing that makes that they might be good at is remembering long-range dependencies. Long range here means, for instance, in the sentence, you see that the fox is brown very early on, and far later, you have to output brown. So in this, you have to remember a span of 10, 12 words or something like this. And RNNs are good at that because of this feedback. In principle, you should, the state of an RNN at some time here depends on the entire sequence of the past input.
There is a question.
Yeah?
So Mark, go ahead. Okay, maybe I will ask on his behalf. So gated, is the gated word same as zero weight?
Can't you just think of gating as setting the weight to 0? How is it really different? That was my question.
Setting the weight, because gating allows you essentially a dynamical mechanism to set the weight to 0.
But doesn't the network already have a dynamical mechanism to change the weights?
Yes. So, one thing I can say, yeah, that's true.
Anyway, maybe it's just technical. I just was trying to understand if there was a difference.
It's very interesting, and I think there's a crucial point maybe that I can make here, which is that without gating, an RNN is in principle a universal approximator. It can approximate any function, and therefore, in principle, perform any computation that you want. What gating really brings to the picture is it allows you to find these solutions. Without gating, it's extremely hard to train RNNs and find these, ideal solutions, which it has to be able to find. I mean, they have to exist. Gating just makes it possible to get there. And it's this mechanism whereby you can dynamically adjust the weights, which makes this possible. But maybe I'll get to it later, and you can ask me again. That makes sense.
Thanks.
Yeah.
Excuse me, can I ask a question?
Okay.
Yeah, so you're talking about gating. Would this be like some equivalent of dropout in feed-forward networks?
Yeah, it's similar, I suppose. But what's the the crucial difference is that with what dropout does is it like kills some weights or kills some neurons, trains, and then kills a different set of neurons, trains, and so forth. And at the end, the idea is that you keep all of the neurons when you, for example, implement or test the network.
Yeah.
And the idea is that it has given you some kind of ensemble of networks. It's like a ensembling method. And I think there's pretty convincing evidence, or like suggestive evidence. But in this case, I don't think gating has this ensembling effect. It's kept throughout, and maybe you can understand it in this way. I'm not sure if this is strictly correct, but you might understand what gating does is for a given input, it allows you to turn off some subset of neurons and use just that network. For another input, it allows you to turn off another subset of neurons and just use that network. So it sort of allows you to access the optimal subnetwork in real time, as opposed to ensembling the network during training. They're related concepts, but they're actually they sound similar, but they have some they're kind of distinct, I think.
Thank you.
Yeah. Okay, and then I don't know if anyone needs this, but I found it interesting because I was working with these kinds of models and playing with them on the computer and on pen and paper. But these gated RNNs, they're used everywhere, not everywhere, but in a lot of places. Like text-to-speech uses a gated RNN to get the intonations right when a computer voice is talking, so it doesn't sound so stiff. Google's neural translation uses this what I refer to as the LSTM, the long short-term memory. That's used in there. Text prediction on your iPhone uses it, and speech recognition. Some incredible speech recognition network that Microsoft trains uses gating. Of course, there's a ton of extra stuff on top of it, but you should understand gating as some very essential component in this larger kind of picture. So it's very useful.
One more question before.
Okay. Okay.
Alex, go ahead.
So I suppose you'll tell us at some point where the intuition comes from, what you should switch off and what you should keep at any task that you have that you want to learn.
So my answer to that would be that I know no human has that intuition. The idea is to let the machine or let the algorithm figure that out by itself. And that's what you would call end-to-end training. So you introduce these gates. That gives it a mechanism in principle to do this selective modulation, and then you let it train. And that's really where the big mystery comes in, because it finds a solution. And now the problem is, as is always the case when you're dealing with large, complex systems of interacting units, you need to figure out why it found that solution. So I would say that's exactly where theory comes into play, to understand why certain units are shut off and some aren't. Now there's some very nice select examples where this is done, and some trivial problem which I'll mention later. It's clear what needs to be done and how you should alter the gates. But in principle, it's still a mystery. There's work to be done there, I think.
Okay, so it's trial and error at some. Yeah.
Exactly. Yeah. Exactly. But yeah,
Okay.
you hope that your training algorithm, like you do gradient descent, you hope that's going to figure it out, and you don't have to. That you just and the onus on the engineer is to feed it the right initial conditions. And so I'll get there. I'm really kind of skipping ahead. But
Okay.
yeah,
Thank you.
right. Okay, and another important point, which hopefully will whet your appetite to thinking about the mystery of modern machine learning, is that what makes the recent advances possible. I think it's quite clear. These deep neural networks, I'll explain what deep means. They scale very well with increasing data and computational resources. So if you have tons of GPUs and a ton of data, they perform way better than traditional machine learning algorithms. And what it requires typically is for them to be insanely overparameterized. So for instance, they'll have millions of parameters. Just to store the weights of the network, you need a few hundred megabytes of data. I mean, okay, but that's a ton, and it should maybe be a little disconcerting because, like, what happened to Occam's razor? The intuition is that overparameterization should lead to overfitting, and that you shouldn't overparameterize. There's also a counter to that, which is that if you overparameterize, you have in principle, larger space of functions, and it's easier to find the function that you need, the network that you need to do the task that you want. And I think this is actually the biggest question. There's a lot of answers, a lot of pieces of this puzzle, but this remains one of the biggest puzzles in modern machine learning. How does overparameterization coupled with whatever learning algorithm you use, how does that lead to such amazing success? But the point that I want to use this for is that large N limits are actually relevant to analyzing neural networks that are used in practice. And large N limits are great for physics, right? You can look at thermodynamic limits and you can actually say things analytically about these networks. Okay. So this is a brief thing about what's next, and where does this field, the physics of machine learning, really fit in? In some sense, it's about the science of artificial neural networks, perhaps. This is just a proposal. So they're introduced, initially as models of cognition, but they've evolved and they've taken off beyond neuroscience, and now are a computing paradigm in machine learning. And as I was mentioning before, their behavior is quite perplexing. And now instead of wet lab experiments, looking at putting electrodes in a mouse's brain, we have numerical experiments. Training enormous networks on multiple GPUs with highly overparameterized networks. But the ultimate goal, I think, is really the same. It's really the initial goal, which is to uncover the computational and dynamical principles underlying learning in large, complex networks of interacting neurons. The idea is that the substrate is hopefully not that important, and I think this concept of universality is quite familiar to at least a physics crowd. So you think maybe whether or not my neurons are in a brain, on a computer, it should not make a difference. I'm still finding out some important principles of computation that underlie learning, and far into the future underlie like artificial just intelligence. Okay, so that's the big kind of sweeping picture. Okay, so that brings me to part two. So I said a lot of words, and now I want to get into a little bit more detail, get more concrete. What is an RNN, and how do they learn? What is the process? And how does physics come in? Okay. So an RNN is a fully connected network of neurons, each with a hidden state H. And each hidden state has some kind of update rule. So it's a dynamical system in this respect. And the update rule says here, for instance, is that H1, this guy, at t+1 is equal to the weighted sum of all of these activities, but then sent through some kind of nonlinearity. So if the really kind of the expressive power of these networks relies on this being a nonlinear function. And there's many choices. I'll stick to just hyperbolic tangent, just so you can just keep that in your mind. That's what we used in our works. It's quite popular as well in practice, although this second one is known as the ReLU, rectified linear unit. This is also commonly used. And another important object, just to define vocabulary, is the weight matrix. So this tells me how much neuron 1 pays attention to all of these other neurons. And in principle, it could be asymmetric. So H1 maybe pays attention to H2. So this direction is very large, but maybe H2 doesn't care what H1 is doing. So this direction could be small. And that's allowed. What I presented in the previous slide was a discrete time simplistic kind of update rule if you have a simple clock register, but you can also think about continuous time neural networks. And this is maybe makes closer contact with dynamical systems. It's quite similar. It just says that the rate of change of the hidden state, H, is given by minus H1. So this just sets, if all the interactions are off, this just says that the hidden state eventually decays to 0. But if there's interactions, it can jump around and do something interesting.
Tankut,
Yeah?
just a question.
Yeah.
Previously, you had the weights inside the weighting function. Now you have the
Yeah.
weights outside of the weighting function. Is that intentional?
It is intentional. I would say there's maybe subtle differences in the two formulations, but by a kind of transformation, you can see that they're equivalent. And it's a matter of taste to some extent which one to use. So you can do either thing.
Also, while we are there, the sign function and the hyperbolic tangent function, the first is just the limit of the second, right? If you scale all the weights to infinity or to very large numbers, not infinity, then the hyperbolic cotangent would become simply the sign.
Yeah, that's right.
Okay.
Maybe I can point out one thing. If you're working with this, you can instead think about applying a phi, applying the nonlinearity to the left-hand side and the right-hand side, and wait, sorry. Let me rephrase. Define a new parameter x, for instance. Oh, I can write. So let me do that. Let's say H1 is phi of x1. And then I put that in there. And so I get phi of x1 is equal to phi of something of j times phi of xj.
Right.
So under an appropriate transformation, it's really an equivalent network in this case. So whether or not these weights are outside or inside the nonlinearity is not a crucial difference. At least this is what I've seen. It'd be interesting to know if there are any examples when it makes every difference, but I don't know of any.
That assumes, of course, that phi is invertible, and that
Yeah,
would be
exactly.
for the sine thing.
Yeah. So it doesn't really make sense in that scenario. You're right.
Okay, please continue.
Yeah. Okay, so it's this continuous time model that I'll be focusing on. I'll try to breeze through this. What does computation with an RNN look like? So I'm saying this, RNNs are computing things, but what do I mean exactly by that? The simplest way to illustrate this, I think, is with this computational graph. So the idea here, you can just imagine discretizing the continuous time system, and noticing that, for instance, the hidden state, H2, only depends on the hidden state at some previous time, H1, and we want to, we have some output. Typically, it's taken to be some linear transformation of the hidden state. So this is the setup, is that at each time, there's some output Y, and to update the state, we go through this arrow, which incorporates all of this, all of these interactions, to get a new state H2, which then has some output. But a computation has an input as well, and the input enters in this way. So for instance, we can just add it linearly to the hidden state. And in this, so what then we'd have is that H2 is updated according to the previous state H1, and also the input X1, and so forth.
Where does this X come from? Sorry,
this is the input. So I'll give you an example. Let's say what you want your network to do is compute the Fibonacci sequence, something like that. I mean, it's not a very interesting example, but what it would have to do, you want it to take 1, 2, 3, 5 and output 2, 3, 5, 8. So then what, for instance, H2 needs to do, it needs to take X1, which is the input at time 1, and it needs to remember X0 through the hidden state H1 and add them in however way it decides to add them, and output a 3. So that's one kind of example of what a computation might look like, and why it might require some memory. Another one, which is quite nice, I think, is sentiment classification. So the input is a sentence from a review of, say, a movie, and the output is either positive or negative, depending on whether or not the review is good or bad. So for instance, here, it receives the inputs, Avengers is not. It's not really changing. It doesn't know yet. What is it not? Then it sees that it's not awesome. So it goes negative right at the last minute, for instance.
Excuse me. Is this reversible, this network? I mean, you gave an input 1, 2, 3, 5, and then you to
you mean
whatever.
in time?
Is that whole thing reversible? Well, if you started as, I mean, the input to output is a nonlinear transformation which you can't go backwards, right?
Yeah.
Is that correct? You can't go backwards.
I don't think so.
Means if you run that whole thing backwards, it couldn't work.
No, typically these RNNs are sort of dissipative systems, if you want to think of it in that language.
And where is that?
Turning back the clock is.
Okay.
Is that?
So you will never be able to know how the network learns, is it? I mean, by retracing itself?
I see. So would you be able to figure out, oh, sorry, how the network learns?
I was thinking you can retrace step by step backwards in some sense to figure out how it learned in some sense.
Yeah, so there's maybe not, okay. About learning that's a sort of separate question, maybe how the weights are updated. But for something like this, you can look at the dynamics, for instance. And this paper here, it's quite interesting because it'll show that they argue that if you train these gated networks on sentiment classification, what it'll find is a line attractor, and what this input will do is somehow move it along with the attractor. So I think this is a very nice example of how you can look at the dynamics and read out some interesting computation, like dynamical behavior that's behind some, computational principle that's behind it, that's doing this, solving this problem. So that's one example of how you might be able to access, maybe not how the weights are adjusted, but what the solution looks like and why it finds that solution. That's
okay.
That's what I can say. Okay, I'm fast approaching the end, but I think I can get through this hopefully quickly. It's a question that's come up. How do you train RNNs? And it has a cool name, backpropagation through time. You've probably heard of backprop. And I think it's easy to motivate with a simple example. The simple example is just the copy task. I get an input at time 0, and I want to output that input. I want y of t to be also x of 0. So I just want to copy it, but I have to remember it for a very long time. So backpropagation is really just defining a loss function. So how close is my output to the desired output? And taking the derivative, updating the weights according to the derivative of the loss function with respect to the weights. So there's some kind of landscape, and I want to move the weights so that I approach the minimum of this landscape. But in principle, this is very challenging because L is not a convex function in J. And that's actually one of the first mysteries of these modern deep learning networks. How in the world is backpropagation finding a good solution in this non-convex landscape? But that's a whole other story. Let's assume that it can. That this optimization works. But there's a crucial thing and a crucial hurdle with training RNNs that has to do with this term here. So it's how the hidden state, the gradient of the hidden state with respect to the parameters. And I'll hopefully flash some equations, but give you a brief like a sense of what they mean. Just some chain rule applied to this object. I have two pieces for the gradient. One just depends on time capital T. But at capital T, the input is off. So the intuition is that maybe that error signal is not very useful. I need an error signal from here. But if I were to try to look for that, I can get that error signal, that's right here, but it's weighted by this term, which is the Jacobian. And the Jacobian is the measure of, is really one of the measures of chaos. It tells you what is the sensitivity of h of t to variations at some earlier time t prime. And roughly speaking, it grows like an exponential. And this lambda L is known as the Lyapunov exponent. So the idea being, if I have small wiggle and it gets very large, the system is chaotic. Lambda L is greater than 0. And if I go back to the previous slide, I see that gradients explode. And this is just untenable. You can't store numbers that are infinite, right? Conversely, if the initial variations die off to 0, lambda L is less than 0, gradients vanish. You lose all the signal from the input and you can't learn. So both of these are terrible. What you need, lambda L equals 0, which is extremely fine-tuned. This is marginal stability. Okay, so training proceeds by gradient descent, but gradient descent has to start somewhere. And that starting point is how we initialize the weights. So you have to choose an initialization. And it's a very good choice. Typical choice is that they're random variables, but you have to choose the mean and the variance, for instance. And this is an incredible observation, is that how you initialize your networks typically makes a huge difference to whether or not they can even be trained. And this is very simply related to this exploding and vanishing gradients problem. If at initialization, your gradients either explode or vanish, then learning cannot even begin. So you need to initialize just right, just at this marginally stable point where gradients neither explode or vanish. And the tunable parameter that you have, I've just sort of taken for granted that it's obvious you need to normalize by n, but take it, this is an important thing to do. The hyperparameter that you have to tune is this G. It's the overall scale of the weight matrices. So this is what an engineer has to set. You want to work with an RNN, you need to pick G. It's not given to you beforehand. And this is what you would look at to pick G. So this is really work that kind of inspired me to think about RNNs by Sompolinsky, Crisanti, and Summers. It's this simple network with n neurons, n is very large, and plotting the Lyapunov exponent as a function of G, which is just the overall scale of J. And you see that for G less than 1, the gradients vanish. In other words, the network has a stable fixed point. And for G greater than 1, the network is chaotic. So you'd expect gradients to explode. So that tells you, if you want to train your RNN, you need to pick an initialization with G equals 1. And I think this is the first example of how you study a physics problem. This is a dynamical system. You apply all of your toolbox, like dynamical mean field theory, to find the Lyapunov exponent, and use this phase diagram to inform, training. What's a good place to start training? But with these simple RNNs, it's just too fine-tuned, apparently, and it's very easily spoiled by once you begin gradient descent. You'll move away from this marginally stable point pretty easily. So this is where gating comes in. I'm grossly out of time, but I'll try to go quickly. So gating,
we started late, so take 10 minutes.
Okay, great. Okay. So we take this simple RNN and we add this multiplicative interaction, sigma of Z. Z is now just a new dynamical variable. H was the neuron's hidden state. Z is some auxiliary hidden state. It's just a copy of the neural network. And sigma goes from 0 to 1. So this was the gating that I mentioned earlier. It's not just 0 or 1, but it's some continuous variable. It's like the logistic function. So we allow it to go continuously from 0 to 1 and give it its own dynamics. So, but what this does, it introduces an additional hyperparameter because we have Zi, the dynamics of Zi gets input from the entire network with weights Jz. And these are different weights, independent weights in principle. So you want to be able to train both Jz and Jh. You want to train the hidden state network dynamics and the gated network dynamics separately. But right, so that has the complication of introducing an additional hyperparameter, which the engineers need to fix somehow. But how does this help with introducing long timescales and giving marginal stability? It's actually, the intuition is very simple. When lambda z is 0, when sigma of z goes to 0 or it's very small, the time derivative of h is very small. And this means that Lyapunov exponent is 0 in this case. So essentially what you have are modes that don't change with time. So kind of frozen neurons in the network. And to visualize this, you once, for instance, had some chaotic trace, some chaotic system where initial perturbations got wild. Now, let's say they start growing and growing, and you apply a gate exactly at TB when the input turns off, and you keep that information indefinitely. So this is the idea, and that allows you to receive gradient signals from when the input was on. And that's really the intuition behind introducing this gate. But of course, you don't want to keep things simple. You want to make it as complicated as possible. And you can introduce an additional gate. And this is interesting. So if this Z gate was like a dynamical time constant, here, an R gate, it modulates this connectivity matrix J. So really what it's doing, it can tell you whether or not it's an additional knob, some dynamical knob that can turn off phi of Hj selectively. So without fiddling with J. So you imagine J is like the network structure, and phi is just some henchman for this R gate is an additional henchman for each hidden state, which shuts it off selectively to the rest of the neuron without adjusting this J. But of course, it also introduces another hyperparameter because we have to adjust this weight matrix, this new weight matrix JR. And the model that we end up with is really essentially a continuous time version of a gated recurrent unit, which is very closely related to the LSTM, competitive in most respects, and also just even much simpler than the LSTM. If you look at the LSTM network, it's kind of overwhelming. There's so many parameters. Okay, so that brings me to the results. So I introduced this gated RNN, and I introduced these new hyperparameters. So just like with the simple RNN, we had some kind of phase diagram showing us how we should initialize the networks and how we should fix the hyperparameters. That's really the first goal here. If we want to apply these our results to machine learning practice. So the first thing to flash is the phase diagram of a gated RNN. And it's considerably richer than the simple RNN. There are regions of chaos, of transient chaos, of marginal stability, and you get this because you have an additional axis, which is alpha r, one of the hyperparameters. So let me briefly go through some more or less interesting features of this, just to pay attention to. So the first thing to notice is this entire region of marginal stability. Now, what do we mean by this? This graph is just showing, this phase diagram just shows G on one axis and alpha R on the other axis. And I have left out alpha Z. Alpha Z is the hyperparameter for the dynamical time constant, sigma of Z. And what this region is really indicating is that I have this entire region where if I tune alpha Z large enough, it's just one direction to change this hyperparameter, I can bring my neural network dynamics arbitrarily close to a marginally stable point. And this can be seen as through the emergence of line attractors. So line attractors here, for instance, what's being plotted down here is, imagine you feed in an input, some kind of impulse. So the network's evolving, and then it sees some impulse. And depending on which direction the impulse is, if the impulse is along some slow manifold, which emerges in this region, you'll remember the impulse sort of for an extremely long time. So these networks in this regime have very long short-term memory. Whereas if it's off the slow manifold, the impulse dies right away. So this is, we tested this idea kind of in very rough preliminary experiments. We saw that indeed initializing in this regime, in this black hatched regime of marginal stability, did two things. It helped reduce the number of epochs, just the amount of time, reduce the amount of time to reach some threshold performance of the network. And it also increased the accuracy that the network reached after completing training. So this is a very concrete prediction, I think, for a new initialization scheme, which was not known before we put together this phase diagram for the gated network. And it kind of aligns with the intuition that marginal stability is good for trainability in RNNs. I'm going to skip that slide. So there's another really fascinating phenomenon, in my opinion, which arises in these networks. And it's not clear what the computational consequences are. But I think it would be fascinating to explore this. And it's something like the following. So imagine I'm going along this orange arrow, and I track the largest Lyapunov exponent. So I'm looking at the transition to chaos. Along the orange direction, the transition is continuous. So I go from negative through 0 to positive. However, if I go along this direction, it's just another way to traverse the phase diagram, the Lyapunov exponent jumps discontinuously to some positive value. So it's negative, suddenly positive. And it's a discontinuous transition to chaos. And the mechanism is quite fascinating, in my opinion. So I'll walk through the phase diagram and show what's going on in this regime from 1, 2 to 3. So in region 1, blue region, there's the network, this huge network gated RNN flows to 0 fixed point. So all the activity will die at some very quick time scale. So you have a stable 0 fixed point. Now we move up to region 2. You still have a stable 0 fixed point, but crossing this green line, there's a proliferation of unstable fixed points. So suddenly you've increased the complexity of the landscape of critical points, but you haven't changed the dynamics fundamentally. Everything's still flowing to a 0 fixed point. And this is actually unusual. Typically, in the past, in other networks, it's observed that the proliferation of unstable fixed points actually coincides with the transition to chaos. But in this network, the region 2 separates these two transitions. So you need to go to region 3 to see a chaotic attractor emerge. But the 0 fixed point is still stable. So for finite networks, finite n, essentially the dynamics you have here is like a leaky billiard. So you imagine you have a chaotic billiard, for instance, for those that know what I mean, but it has a hole in it. So the particle enters, moves in this chaotic way, and then finally escapes to the stable 0 fixed point. But it has some kind of lifetime to stay in this attractor, which is actually a repeller in this case. And that lifetime increases with system size. So in the thermodynamic limit, infinite n limit, that lifetime is infinite as well. So this is what gives rise to this discontinuous transition to chaos. And you have this interesting situation where you have a stable 0 fixed point and a chaotic attractor, a chaotic repeller with an infinite lifetime, basically. And finally, proceeding further to region 4, you just get chaos. It's all chaos, nothing else. Unstable fixed points abound, and the chaotic attractor is stable. The 0 fixed point is no longer stable. So I think it would be fascinating to explore this regime further. This phase diagram, as far as I'm concerned, is unexplored in the machine learning setting, and I think this is a very exciting, future direction, at least for me. So if you have any questions or comments, I know this Zoom setting is maybe not conducive to that, but please feel free to send an email if you want to follow up or chat some more. I'm happy to chat.
Yeah. Thanks, Tankut, for this wonderful talk. Okay, so are there any questions?
Yes, I have a quick question.
Yeah, let's go ahead.
Okay.
What's the actual difference between the region 2 and 3? Is
Let me see.
it the time scale? In region 2, when you have the unstable fixed points, they have a finite lifetime, but in 3, the chaotic lifetime is infinite, meaning it takes infinite time to escape, get to the fixed point. Is that the difference? The stable fixed point?
Yeah, exactly. So the difference between 2 and 3 is the lifetime, kind of being stuck amongst these unstable fixed points. And
right.
once in region 2, that lifetime doesn't scale with n, doesn't scale with system size.
So that's what I was going to ask. Large n limit, 2 will vanish and it will be only 3?
2 is still there. Yeah, the region 2 doesn't.
But 3
depend
disappears.
In the large n limit, these demarcations still exist, but really the only difference, the crucial difference is that in 2, you might say the lifetime doesn't scale with n, remains finite and rather small. The transients have a very short lifetime. In region 3, the transients have a very long lifetime, and that lifetime grows with n.
Okay, thanks.
Yeah.
Any more questions? So Tankut, I have a couple of questions. So,
Okay.
so there is an example. I don't know. I can give you an example of such a discontinuous transition, and maybe you can tell me if it fits into
Yeah, I'm
what.
fascinated. Okay.
So think of a Landau level problem on a hyperbolic space,
Okay.
right? So if you think about the spectrum, so you will have this whole parabola of filled parabola of continuum states, which are like exponentially diverging, right?
Yeah.
But then what happens is that at some, this is the energy versus the magnetic field. So at some, and if you go along the magnetic field x-axis, then at some critical value of the magnetic field, a Landau level peels off that continuum, right? And these Landau level peeling off is like a bunch of cyclotron orbits which are not chaotic. So now if you follow that Landau level all the way to its point of merging into the continuum, you can think of that as like proliferation of unstable fixed points because it is merging into this continuum, right? Would you characterize that as like a discontinuous transition to, because it's like there is a Lyapunov exponent is 0 for that, for the cyclotron orbits.
Yeah.
But then as soon as the curvature wins over magnetic field, you just like proliferate into this continuum where every point is an unstable point.
So
It means I should not use the word fixed point because I'm talking about a Hamiltonian system.
yeah, and I see. So first of all, I don't know how to think about Hamiltonian systems yet in this context, but so
maybe you can just supplement them with their negative counterparts, right?
Yeah.
So every Lyapunov will have its negative partner, let's say.
Yeah, right. So you're saying you have 0, 0, 0, and then abruptly positive?
Yeah, so it's basically, so if you are in a negative curved space, so all the trajectories are exponentially diverging. But if you stick in a magnetic field at some critical value of magnetic field, which is kind of dependent on the curvature, you kind of trap a cyclotron orbit there, right? So in the energetics, it looks like this, that you have a, maybe I don't know if I can annotate or not.
Oh yeah.
Maybe not. I don't see the annotate button, but never mind. So the point is that you have this parabola, filled parabola, where every point inside the parabola is a state which is kind of exponentially diverging trajectory for all those energies. And at some critical value of magnetic field along the x-axis, Landau level peels out of that continuum, basically. And then if you keep going, this is like a parabola with dendrites sticking out, which are Landau levels.
Nice, dendrites.
Yeah, dendrite with only one branch. So then if you follow the dendrite, right? So it's 0, 0, 0, 0. And then as soon as it hits that critical value of magnetic field, it just boom, explodes into the continuum. And then suddenly there is a non-zero Lyapunov exponent associated to that trajectories, right? Bunch of them.
Interesting.
Yeah, maybe this is like just a thought that maybe this is an example of a discontinuous transition within a Hamiltonian system.
I'll have to follow up with you. Is it an issue of commensurability somehow?
No, it's just like a simple dynamics Landau level problem on a negative curved space. You know all about it. There's like this SL2Z, SL2R symmetry, right? So yeah, okay, maybe we can discuss separately. But another question is that this gatings that you introduce, like let's take about sigma Z and forget about sigma R. I have less intuition about sigma R. But sigma Z seems that you're kind of coupling your system to an additional bath, where this bath is this bath is performing some necessary job for you in order to kind of freeze certain modes.
Yeah, absolutely. That's
it's more like this colored noise dynamics, right? So what happens is that you have a frequency dependent friction in some sense, let's say, and depending on what profile you fit, your certain modes are damped more than the others.
Yeah.
right? It's like some kind of a colored noise dynamics that at least the sigma z seems terribly familiar to that.
Exactly. If you want to integrate out the
Yeah, exactly.
the Z gate, yeah, presumably what you're left with is the usual, you know, the dynamics for H, but with
Some additional noise or not.
yeah, right. It's not clear what kind of noise, because sigma z is sort of this multiplicative interaction, and so I don't know if you could reframe it as a additive noise. I think
But
most likely,
maybe you won't get a Markovian one, but you can get a non-Markovian effective noise, right?
that's essentially the case with RNNs. RNNs are highly non-Markovian. Just a brief sentence, you know, the way we deal with these systems analytically in theory is by developing a dynamical mean field theory. So that's really replacing all of the interactions, this J times phi of H, replacing that with some effective noise term.
Right.
But that noise has correlations in time.
Right.
It's non-Markovian. And if you were to do that with the Z gate, this sigma of Z, for instance, it multiplies the whole thing. It's like a Gaussian process, sigma of Z, which is a Gaussian process, multiplying just an ordinary kind of Langevin dynamics.
Right. So what I'm saying is that if you plot some autocorrelation function for H,
yeah,
two-point function, and see it in the frequency space, you will have some profile, right?
Yeah.
So this sigma z looks like as if you're taking a frequency window and just freezing them out by putting some frequency dependent friction additionally, which you have to fit against some requirement.
Yeah, that's probably a good way to think about it. I'm not sure if it's, you know, useful in the sense that
right.
you do anything, but yeah, I think that's
yeah.
That makes
okay,
sense.
so are there any more questions?
I had a more like engineering question. What tools do you use to construct your RNNs? Do you use possibly TensorFlow?
Oh, yeah, or this TensorFlow works. The experiments we did, if I can get to it, the experiments we did here were in PyTorch.
Okay.
There's ways like okay. Oh my God. Yeah, the GRU, which I mentioned, the GRU and LSTM, these are standard architectures.
Yeah,
absolutely standard. I think there's built-in classes in PyTorch. You just write it, neural network, GRU or LSTM, and you know let it run.
Okay.
Yeah.
Would you recommend that for like research purposes? Because I've been trying to construct RNNs that are not standard, and so I've been trying to use TensorFlow because basically what I'm trying to do is construct an RNN that it's not like a GRU that the cell contains all the dynamics, but basically I'm looping regular cells together. And one of the ideas, just like a feed-forward network can fit in any function, my idea might be that the loop of neurons, or regular neurons, computational neurons, might just fit in any type of recurrent cell, just like a GRU, LSTM, and so on. So my question is, which one of these tools do you think it's better for these types of research? PyTorch, TensorFlow, or is there maybe something else out there that you can recommend?
For your designer RNNs?
Yes.
I'm not sure. I'm not sure how flexible they are, but I think they're pretty. If you dive deep enough, you can I mean, I would just do it from scratch, but that's probably the least effective way.
Yeah.
Like you want to scale up and test it with enormous networks.
Mm-hmm.
Yeah.
Okay.
I think PyTorch and TensorFlow, it should in principle be possible to bend them to your will. But
Okay.
you have to put some effort into it. I'm happy to talk about it more.
Sure.
Later
All right. Thank you.
Yeah.
Okay, so let's thank Tankut once more. Okay, so thanks Tankut for doing this.